and get going on assignment 4. So last bit about NumPy, since NumPy is where we're going to live, and two things, which is going to be sorting and file I/O, so reading in information. So let's switch this on. You'll notice this with, so we did the third Jupyter Notebook. We now know what a NumPy array is. We're quite comfortable with that. We're quite comfortable with NumPy random, so we can populate an array, so we can make our own data. But what happens if we want to actually get other people's data? So the whole idea behind this class is that somebody gives you data, and now you need to do something with it. So casting, sorting being, how can I order my data, and matrix operations, which is very useful if you are starting to think about machine learning, which is essentially just all matrix operations all the time. And the simplest file I/O there is. So NumPy built-in file I/O is like I/O input output, by the way, if I use a term that nobody's heard of. File I/O is the simplest way to get the data into your Python program. There are others, but the NumPy one is the one that's always available to you. We'll talk about file types for a minute. OK, so an array, list of numbers, strings, or any other variable, data sample, time series, any kind of, this is what your data looks like. And there are much more sophisticated stats packages in Python, SciPy, Pandas, et cetera, but NumPy is sort of where we get started. If you want more stats, go to R. If you want faster things to happen, use Julia. But honestly, Python gets you there 90% of the time, 99% of the time, I would say. So we'll start up using SciPy and other stats soon. So we can initialize data with just zeros, ones, or nothing. And we tried the nothing last week. And you may have noticed that nothing wasn't empty, because that was the value that the bit had while you pointed at it. Remember that Python is pointers. So it starts by pointing, like the initialization says, this is the point in the memory where the value lives. And so if you say ones and zero, and it's like, oh yes, and the value is 1, or the value is 0. But if it goes empty, it goes, this is where the value lives. I haven't put anything in. That's up to you. So if you print that, it's going to be this gibberish of very low numbers or very high numbers. So conditional arrays allows you to then filter that. So you can say, like, OK, where is this statement is true, is none, and is inf are important, because not a number is something that you want to know, and inf is where you accidentally divided. OK, so mask versus where. Masks return an array with true or false values, so you can use one or more conditions to be met. This is great. So you can have masked arrays, for example. So you have an array, and then you sort of white out the values where this condition isn't met, for example. The values still live there, so you still have it. It just goes nope for that, right? So it sort of shutters you. So it just gives you the data that you need where this condition is met. For example, I don't trust Jeff's measurements, so I'm going to go where observer is Jeff, and Jeff just disappears, like all the Jeff points just disappear, and I'm going to see if that's any different from the rest of them. So you can do things, you can select subsamples, or you can just sort of white out things. A mask is still the same length, so that's the useful part. The data is all still there. It's just there's an additional array of yes, no's, like if this condition is met or not. OK, so if I do where, like, so I do between bracket NumPy array, between bracket where value is greater than 0, then I'm getting a shorter array where I've just literally cut them out. See how the difference works there? OK, all right. I know, it's Monday. So matrix operations, right? So you can do things like where you multiply a matrix with a vector and then get the new vector. Or, of course, this is at XKCD, so this is not what you should get. But you can do things like very simple operations like addition. You can do things like multiplication. element-wise multiplication, or you can do a dot product, which is really nice, right? So if you want to do dot products, convolve one thing with another. If you, for example, have, here's a sea of data, and I want to convolve everything with a Gaussian, essentially smooth it. That's just one, I have to make an array with a Gaussian distribution, but then I can just do this dot product, and there it is. So if you have to do matrix operations, NumPy is your friend. And so you can also do things like transpose, or just simply do a dot t, capital T, and it just transposes it like that. It's just flip, because it is very quick at that, because it's not, a NumPy array is not just values in the, not just values in the memory, it is a pointer to that value. So it literally just switches the pointers. It doesn't even read it out and reread it in. It just goes, okay, well, I just need to transpose. So whoop, there you go. This is the kind of stuff that is very nice if it's quick in for things like machine learning later in life. So this is why NumPy is sort of sitting. NumPy is sitting at the rock basement. What is it? Foundation. There, foundation for machine learning, right? These kind of things like dot products and transpositions are fundamental to machine learning. So that's why these are in there. So NumPy matrix, many built-in functions, some diagonal, very, very, very useful if you just want to go like, I just want, like, here's my, like, how many values are in there total? Just sum the whole thing, or sum in one direction. So you can just get a column with everything summed together. And so this is a very useful tool in statistical tests later, foreshadowing. SciPy gives you a covariance matrix. So it's actually like how much correlation do you get with each parameter. Like you have 12 on this and 12 on there, and like you want to know what the diagonal is, for example. How much quantum mechanics have you been subjected to yet? Okay, because I didn't see anybody start twitching as soon as I said covariance matrix and things like, diagonal. That's the kind of thing you need a lot for when you're actually reducing the dimensions in quantum mechanics. Okay, it wouldn't be a proper talk it wouldn't be a proper lecture if there wasn't a couple XKCDs in there. I realized that the matrix came out 24 years ago, so I think it's before any of you were born. But still, I think you've watched it at some point. It's such a cultural icon at this point. So yeah, there's a whole, like, you don't know what the matrix is. It's like, well, yeah, no, it's just array of numbers. What? Maybe you just suck at explaining. Please don't tell me that later. We talked about typecasting, so use one array of one type into another, use with extreme caution, but it is there. And so NumPy as array or with array as type, turn a NumPy array into another type. So you can have like a NumPy array and just type in as type float, for example, which means you've just sort of taken a baseball bat and rammed it into that shape. It's usually some violence was involved to that NumPy array, okay? So it's the kind of thing where you go like, I accidentally read it in as ints and it should be floats. Should have you not read that in as ints to begin with? Maybe that's something to fix earlier on, but I cannot say that I have not been a user of this. I have used this, so there you go. Sorting. So now that you have your NumPy array and you have your data, you might want to sort, for example, by timestamp. You might want to sort by temperature. You might sort by one of the columns in your data. So you go like, okay, now I want everything sorted by when the data came in. That's like, there's a time thing, like first part of the hour, last part of the hour. Suppose I'm getting I'm being super obsessive and I've given out a test and I'm getting everything back, and I'm actually writing down the number on there when I got the test back, just to see how long everybody takes with the thing. So then I want to, of course, sort who got it first and last. So there's two ways to do that. You can just do NumPy sort, which just gives you the array back sorted numbers. So for example, if you have a series of random numbers and you just want them in order and there's no other numbers or other parts of the array, then you can just do NumPy sort. Then there is, then they've neatly sorted that The NumPy arcsort is, for example, when you say, okay, which is the order of the point in the matrix that, like in that NumPy array that I need to go. So instead of, for example, I can sort by one column, and I can say like, okay, this is the timestamp column, but I want the names sorted in that order. So it just gives me back the position I need to jump to into the array to get a sorted array. This is very useful if you want to sort one array based on another array. I want you to give me the list of names by the time of returning of the grade, or the returning of the exam, or sort the names by grade or length or something like that. Who here has heard of the kind of sorting algorithms that exist? This was like, for computer science, it was like sort of the holy grail in the early 80s. Like, how do I do this efficiently? How do I sort things quickly? Maybe you've been part of a team where, you know, the coach says, okay, I want everybody to, you know, sort yourself by length. This is always a fun one because you can always have like people go like, no, I'm taller than you, right? So it's just, especially these size people. So if you say, okay, sort by length, what's the quickest way to do that, right? The quickest way is to basically all go like, all right, you're the tallest, you go stand over there, and then everybody sort of swaps until you've got your little sorted by length, right? And the bigger the sample, the bigger the class is. The longer this particular argument takes, right? If you do this long enough, if you have a big enough class, it'll end up taking all of PE, especially if you do it right. So you have different ways to sort these things, right? Let's see if the little movie. You can, oh boy. I really wish that these things didn't come with like their own techno track, because I could do without that. But there's selection sort, where I basically grab something and figure out where it should go. Like, so basically like, okay, what's the next one? No, that one, and then move it over. There's bubble sort, which essentially, well, this is super fast. I usually end up playing this video a couple of times because, as you can see, the first thing to take away is that different kinds of sorting algorithms are very, very different in speed, depending on the kind of data that you get. So, yeah, cocktail sort is literally like, that's the cocktail waitress that's walking back and forth between and taking your order and putting it in the right. You'd think that'd be fast, but it's like the second to slowest that exists there. So there's quicksort is essentially what we've ended up with in NumPy, because as you have noticed, this has been green for a while now. So that was the one that won. But there are many different ways to sort your data. So it depends, and that's what I kind of want to, the merge sort sort of sorts a smaller part and then moves it into the total. And so if there's only a few values, that's actually pretty quickly. Like, notice that that is different. Like, depending on what kind of input data you get, you sort faster with different algorithms. And, you know, that is a thing that the cocktail is always, like, really, really slow. And you think once you hear that, you're kind of like, yeah, you move the smallest, biggest, and you go back and forth. That should be really fast, right? No, there is ways to do this much quicker. So usually by literally just going through and swapping, and then swapping again, and then swapping again. Bubble sort being, you know, nice and slow. So we never use bubble sort ever again. But it was one of the solutions. Now, if you have something where it's like, yes, it was ordered, but the wrong way around, how do you flip that? So you see something like heap sort is one of those flip algorithms, and it's actually much quicker there. Once again, cocktail is always the loser. You kind of go like, so why are you even illustrating that? It's like, because it wasn't clear what was the best sorting algorithm for quite a while. But now we have, so for NumPy, we basically landed on quicksort, and you can do heap sort as well. So if you kind of go like, I think my data is mostly sorted, then heap sort might be faster. This is only important when you have a small computer and a huge data set. These are relative terms. But it still is a thing that, you know, in the early days of computer science, and still, right, these are the kind of things that make your sorting all your big data, for example, it's back into important again. Like, it depends on how much computing power you have versus the size of your data. Okay, wow, bubble sort is still at it, as is the cocktail one. So there's two things that I want you to notice. Like, there are different approaches that you can sort your data, and it depends which one the fastest is, depending what kind of data goes in, right? So these were almost sorted. Here, insertion and quick sort. Quick sort is always a good second, which is why we ended up with it. It's a good default, but there are other options. And hey, the cocktail one was done really quickly. So if you've almost sorted data and you just want to check it, the cocktail is actually not so bad. So it depends a bit on what kind of data you get in. However, most of the time, it'll just be a randomized mess. So quick sort, it sort of is. But I want you to understand that it's like, why is it taking so long? This might be it. This is true for other things as well, right? So but sorting is the best example. And there's always one where you sort of have to wait, and I just have to dilly-dally for a moment. And there we go. So let's see. We had selection sort, shell sort, insert, merge, quick, heap, bubble, comb, and cocktail. All these different algorithms, some of which are implemented in NumPy, some of them people didn't even bother with anymore. So this is quicksort. We use quicksort. It will do the best shows most of the time, unless the list is almost sorted. So if you have something where somebody just inserted one random value somewhere in your data, it's going to take a little while. Fine. Everybody works with computers that are so fast that unless you are dealing with something that strains the memory, it's not going to be an issue. Heap sort and stable, they weren't included in, but so those are other. Heap it was, but insert wasn't. What was it? Stable wasn't. Okay, I cannot overstate this particular thing. I know I've said this before with floats, I think, but copy versus deep copy. If you copy, if you refer to A, any changes in B are now reflected in A. So if I do anything in B, like multiply it or divide it, then A also reflects that. This is because B is just pointing at A. It's the same chunk of memory. Okay? This is really frustrating if you don't know this or forgot. And I say that because I've spent a very entertaining week, subtext, not entertaining at all, finding this particular error in my own data, in my own code. So changes, so use NumPy copy. Now this is a separate array. If I use NumPy copy of A, now it's a separate array. I can do things to it and then compare the two. Copy versus deep copy. Can you take a look at this bug? It just opened. Uh-oh, is this a normal bug, or is it one of those horrifying ones that prove your whole project is broken beyond repair and should be burned to the ground? Option B. It's a normal one this time, I promise. Okay, what's the bug? If the server crashes, if the user's password is a resolvable URL. I got the lighter fluid. It's basically, I had to rewrite the code because like somewhere I was not using NumPy copy. It's not a bug, it's a feature. This was a choice way at the beginning to not allocate a new chunk of memory every time. However, if you forget that, it can be really frustrating to fish out. It's because of the memory usage. So I know that I've mentioned this before, but it's like memory usage, if you want to be efficient, you point to the memory. You don't actually ingest the memory into your working memory every time. And only allocate arrays when you need separate ones. And otherwise, you know, it goes there, point to it. Everything is a pointer in Python. This is, again, a fundamental, you know, so like locations in memory. That is the fundamental idea. File I/O. Okay, fine. We're going to go read our data now. NumPy has a native file input-output module. Gen from text and save text. These are, you know, this is get it into your memory, into your program. This is save it out. We are deeper into data ingestion models like AstroPy ASCII and AstroPy tables or the Pandas packages. Yes, then you have many more options. But this will do if it's just a text file. This will do if it's just a CSV, comma separated value, or TS. tab separated file, TSF or TSL? I don't know. Starts with a T. TS something. I think it's TSF. Nobody sees that because you always see like a text, but it's a tab separated file. There is some weird. So if you look at your keyboard, there are a bunch of things we don't use for text as much, and there's a bunch of characters we don't use for data at all. And some things like the horizontal bracket, horizontal bar, for example, vertical bar, for example, or the tab or the comma are good ones to separate one column from the next in just a text file. And these are the kind of things that you can save it with or generate it from. For now, everything can be done with text files. This is great, and honestly, we should all stick to text files for as long as possible, because if anything fails, you can just load it up in like the simplest text editor and see if something went wrong. I've done that many a times where I go like, oh, the return, like, there's a weird character here that if I just cut that out, it's fine and everything reads in. There are other things that you can read in. There are many new kinds of data standards, but there's TeX, that's LaTeX, PDF, CSV, comma separated values, text, that's just plain text. XLS and .xls those are Excel sheets. So, and often you can read in an Excel sheet as well. But they are, the CSV is sort of like the old version of the Excel sheets. Anybody here work with Excel? Anybody forced to work with Excel? Right, okay. So that's where data entry often happens, right? And so you can end up reading those in. PNGs, PowerPoint, JPEGs, and GIFs, those are not really anything that but you can read them in. Those are data. You can actually get the values of the pixels. So how did we end up with so many different ways to put data in a file? Well, this was basically what happened. It's no actual, I don't find this joke funny anymore because basically this is what happened. There are 14 competing standards. Oh no, we can't put the metadata in properly, or we don't have our particular flavor of data. We don't quite like the people who make that particular thing. Whatever, there are now 15 competing standards. It just always seemed to proliferate rather than, converge. So this is why, for example, astronomers are going to go like, no, you can pry FITS files from my cold, dead hands. I will just stick with these things because I understand them, I know what goes in them, and all my computers, like every piece of code that I have, knows how to read them in. So yeah. And then, HDF5, for instance, comes along. It's like, yeah, this is much better at handling giant tables. I'm like, Don't care because, it's, I don't know, it's a new standard. It's another one that I have to read in. It comes from a different area of computing science. I'm sure it has fantastic reasons to be great, but 15 standards no longer. Okay, so read all these standards. So you're kind of like, okay, gen from text is literally, it says generate from text, so it's just text files. If I want to read anything else, well, us astronomers use Python AstroPy tables, but the pandas package is absolutely wonderful here. It reads in CSVs, text files, tabulated separated values, Excel sheets, you name it, you now have this data. I had a colleague, for example, who helped his biology colleague because they had apparently typed in every piece of the information in Excel sheet after Excel sheet after Excel sheet. So basically, they loaded up their data and Excel crashed. So he was like, well, why don't we read it in Python? And he was like, boom, here it is. Here's the analysis. There you go. And they go like, this has taken us months, and we weren't getting anywhere because Excel kept crashing. This is the nice thing about that. You can get everybody's legacy data and just ingest it and work with it. So Panda is a wonderful extension after this class, so to speak. So, okay, I'm speaking way too fast, but we can get started on exercise 4 because I want to get into data visualization soon. So we have the simplest file I/O on hand now. This is what we're going to play with in assignment 4. And then we get to my favorite part, where I have very strong opinions, loosely held, about data visualization. So how to now, because now you have all the tools at your disposal. You have basic stats. You know how to get your data from the text file into your Python program. You know what kind of types it are. You can figure out how long it is. You know what built-in functions you have available. You can do mathematical operations on all of these. You have everything except now I want to show. And if this is sort of like a very important part of data, of science in general, as soon as like I have the data, I see so many people throw up a table. I'm like, I can't turn that into anything in my head. Give me an X and Y plot, right? Show me, not, ask me to do math in my head while you flash a table. Like, look, we have data. It's like, fantastic. What do I do with it? I've sat through a bunch of computer programmer or computer science talks, and the number of people who flash up a table to show that they have data and then show a picture of the computer. I'm like, that's helpful. Your computer is great and mighty. I got it. So the whole point is that you now want to boil it down to the essentials without lying to your audience. So that's what we're going to talk about next week. How to actually visualize this data. This is a huge part. Like, we now have the basic tools. We can say, like, oh, it has a Gaussian distribution, or it has a standard deviation, has a mean, mode. I can tell you all these things. I can sort everything. I got it all from a text file. I know what it is. So I can do data operations, but now I need to actually show you what it is. And it's such an important step of actually understanding what kind of data you have. Okay. Fantastic. So we can get started on assignment 4, or some of you already have, and then I'll walk around, stop the recording now, and I'll walk around and help you all. Yeah? Cool. On Friday, I want to chat about the midterm. It is never too early to start about the midterm, about the kind of data visualization you want to talk about, because this is going to be